Hello everyone, I'm Liguang Zhou, a PhD candidate from the Chinese University of Hong Kong, Shenzhen. I'm also working at Shenzhen Institute of Artificial Intelligence and Robotics for Society. I'll present an ICRA 2021 paper, Long-Range Hand Gesture Recognition via Attention-Based SSD Network, in this video. The presentation mainly includes these 6 perspectives. Let's start with the motivation. You can observe these 3 figures in the slides, showing the person is interacting with various devices. The first figure shows a person is interacting with a mobile car in the game. The second is a doctor uses his hands to interact with the organs in the computer. The last figure shows a person driving a car and uses his hand to send a command to the vehicle. The same thing here as the interaction range between person and machine is relatively limited, is within 0.5 meters. Since the previous demo shows the human-robot interaction at a limited distance, we raise a new question: can we do long-range human-robot interaction via hand gestures? For example, the following figure shows the human is raising their hands to interact with the mobile agents at a longer distance, like more than 5 meters. To this end, we start to do the literature review WRT this particular problem. In this figure, we observe that a man is raising his arms to interact with the mobile agents. Since the arm posture occupies a relatively large area compared with the hand, it is possible to interact with the mobile agents at a longer distance. However, the interaction distance is still less than 5 meters. In this paper, a human driver is driving his car in simulation and can use his hand to communicate with the car in simulation. The interaction distance between driver and car is limited by hardware and algorithm. There are 2 papers published in IEEE 13. The left one shows 4 people are raising their hands and send the command to a quadricopter. The right one shows a person is sending the digital number to robots via hand gestures, both of which are limited at the interaction distance. The interaction range of the left one is about 1 to 2 meters, while the right one is less than 1 meter. This paper is recently published in IEEE 18. The person is sending the command to a dual-arm platform. The same thing from here is that the limited interaction distance, within 2 meters. In summary, all of these systems are not sufficient for the interaction between humans and WAVs at a longer and safer distance. To solve the long-range hand gesture recognition problem, we need to build a dataset by ourselves. First, we refer to the paper shown in this figure, where a self-built dataset for American Sign Language recognition is presented and open-sourced. The problem of the ASL dataset is that the person is only sitting in front of a USB camera within 0.5 meters. To provide the long-range hand gesture recognition ability, we try to extend this dataset by building a dataset with the person performing hand gestures at multiple ranges, for example, from 2 meters to 7 meters. This figure shows the dataset we are collecting, and there are 8 people in the dataset. Each one is performing 10 different hand gestures at multiple ranges. The dataset is open source, where you can go to the website to download the dataset for research purposes. The left part of the slide shows the number of images in the training set and test set. The long-range hand gesture dataset is of multiple ranges, where there are 3024 images as the training set train_mx and 1296 images as the test set test_mx. Besides, we take extra 543 images from the test set as test_ms, meaning hand gestures are collecting from short range, and 504 images from the test set as test_ml, meaning hand gestures are from long range. Moreover, we construct another single-range dataset from the multi-range dataset, as tiny hand and median hand, where the hand area distribution of these 2 datasets is displayed in the right figure of the slides. The tiny hand dataset is the hand gestures with an area between 200 to 1000. The median hand dataset is between 1000 to 4000, while the dataset from the ASL is between 5000 to 20,000. To recognize the hand gestures at such a small size, we resort to the help of the SSD network according to literature, which indicates the SSD performs better than YOLO on the small object detection. This diagram shows the previous work, which contains 2 cascaded SSD networks named SSD1 and SSD2. SSD1 is used for head-shoulder area extraction, and we assume we can find the hand gestures in this area in most cases. SSD2 is used for hand gesture recognition. It not only locates the position of the hand gesture and determines the classes of hand gestures. However, It is low efficient to recognize hand gestures with two SSDs, and it takes more labeling work since the bounding boxes of the hand shoulder area should be labeled firstly. This diagram shows our proposed attention-based SSD network. We incorporate the CPOM module into the network at 6 different positions ranging from 0 to 6 to refines the feature map individually. The CPOM module is composed of a channel attention block that refines the attention alongside the channel dimension. To enhance the feature map further, a spatial attention block is connected after channel attention. This is the qualitative results of the proposed method with SSD and joint SSD, where both the SSD and joint SSD fail to localize the hand gesture, while the CPOM SSD successfully localizes the hand gesture. In Table 3, the results show the proposed method performs surprisingly well than SSD on the long-range hand gesture recognition, short-range hand gesture recognition, and multiple-range hand gesture recognition, indicating the excellence of our approach. Table 4 shows our method has a similar number of parameters with SSD and performs much better than SSD. Besides, even though the joint SSD has twice parameters as CPOM SSD, but it has worse performance on the same dataset. Both experiments show the effectiveness of the proposed method. Table V shows the performance of the proposed method on the median hand dataset, where our algorithm outperforms the SSD. Table V shows the performance of the proposed method on the tiny hand dataset, where our algorithm outperforms SSD with a significant margin, suggesting that the proposed method working well on both median hand and tiny hand recognition. As Tab 2 shows that the proposed hand gesture recognition system has 3 benefits compared to other hand gesture recognition systems. The first one is that the proposed system features the recognition of small hand gestures and recognizes the hand gesture up to 7 meters. In contrast, most of the previous systems are mainly interact with hand gestures within 1 meter. Compare with the Skeleton plus CNN that reaches up to 4 meters, which is limited for interaction with mobile robots. Besides, the Kinect V2 sensor is required, which is not lightweight and has a limited depth sensing ability, 4.5 meters. In contrast, our system can interact with hand gestures up to 7 meters, which is long enough and safer for interaction with WALBs. The third benefit is the speed of our system reaches 28.3 fps, which is 5x faster than the Skeleton plus CNN system. We have also developed an Appleton game that is used for practicing the American Sign Language for beginners. We release a dataset, namely Long Range Hand Gesture, LRHG, dataset, which features the small hand gestures collected at long range by a lightweight USB camera, enabling the interaction between humans and robots at multiple ranges and long range via hand gestures. To solve the novel long-range hand gesture recognition problem, we incorporate both the spatial and channel attention mechanisms into the SSD network with a CPOM module, namely CPOM SSD. Experiment results show the proposed CPOM SSD notably outperforms state-of-the-art methods and recognizes hand gestures collected up to 7 meters. Thank you for listening.